Okay, now section 13.7, tangent plane. In this section, we introduce tangent plane to a surface and look at how to find its equations. Tangent plane is extension of a tangent line to one variable function y is equal to f of x. This shows the tangent plane on the surface at this point. Okay, this is a generalization of the tangent line to the multivariable function. A vector equation of the tangent plane can be obtained in this way. This is so as you see, from this surface we can find the directional derivative at that point and the normal vector at the given point. Then tangent plane can be obtained as a arbitrary point x, y, and z, and if this is original, if this is x naught, y naught, z naught, then with the arbitrary vectors on this plane, then we subtract from this one to that one, which gives us this vector, the r minus r0, which is x minus x0, y minus y0, and z minus z0. And with this vector times the normal vector of this plane is orthogonal. So inner product of this gradient vector with this vector is equal to 0. That's what the equations comes from. We can summarize it in this way. Let P be a point on the level surface on this function, this level surface f, and where gradient f is not 0. Then the equation of the tangent plane at P, this point, this tangent plane, the blue one, is the set of vectors x, y, and z that satisfies this equation, which comes from this, isn't it? The inner product, the normal vector of this plane times the vector on this planes are orthogonal, and thus all the vectors that satisfies this equation, which can be written in this way. So this is the definition of tangent plane. You recall that if y is equal to f of x be a differential function of one variable, then the equation of the tangent line at x is equal to a was given in this way. Now in three-dimensional space, the equation of a tangent plane is generalized in this way. Okay, so the equation of tangent plane is a natural generalization of the tangent line, as you see. Find the tangent plane to the surface g is equal to 9x squared minus y squared at the point p naught, point 1 to 4, is this. Okay, find the first partial derivatives of f with respect to x, y, and y, and then we have a point, the normal vector so we have, and at the point 1, 2. Okay, so what we have, and the partial derivative of f. Okay, so we just plug in those points. F of a b is equal to 4, and point is 1, 2, and 1, 2 located here, and the partial derivative of f with respect to x at the point is minus 2, and partial derivative of f with respect to y at the point 1, 2 is minus 4. This gives us the equation. This can be visualized here. Okay, so I made the code for that problem. We have this is the equation that you have, that we just checked here. Minus 14 minus 2x minus 4y is obtained in this way, as this equation is given and partial derivatives given, and I gave an equation for the tangent line, tangent plane, which is obtained here. If we draw it, and it gives like this, this shows the tangent plane, the blue lines, at the point on the surface of the equation that we had, like this, g, 9 minus x squared minus y squared. So, and find the equation of the tangent plane to the graph of the sphere. Okay, if we have a sphere like this, and we are looking for a tangent plane at this point, like this, then we find the directional derivative, the partial derivatives with respect to x, y, and z, and then then the inner product of these directional derivatives at this point, 2, 3, 1, to gives us, which gives us the tangent plane like this. Same thing. And the normal lines. Let g is equal to of function of the function of two variables x and y, and then the gradient to the surface g is equal to of x or xy at the point x naught y naught g naught is given by this implicit differentiation that we've seen, where capital F of x y g is given this way. Then the normal line of this can be written in this way with in the parametric equation format, and in like this in the symmetric equations format. Okay. Okay. G has been moved to this way, so f of x y minus g, and we wrote it as a capital F. The partial derivative of capital F with respect to g is minus 1. That's why this is minus 1. Okay, then use this information, find the tangent plane and the normal line at the point P naught to the surface of this. And like you see, this is a surface, and this is the equation of directional derivative, the equation of the tangent plane that you see here as a blue lines on it, which is obtained as at the point 1, 2, and 4, and the directional derivatives are, the partial derivatives are minus 2, because the partial derivative of that, with the capital F with respect to x is minus 2. Partial derivative of capital F with respect to y is minus 2y, but you plug in 2 there, so minus 2 times 2 makes it minus 4. And partial derivative of the capital F with respect to g is minus 1. So that gives a minus 1 here. That gives us this equation, which has a tangent plane, which can be written as a parametric equation like this. And next example, find the tangent plane and the normal line at the point of this and this surface. Do the same thing. Yeah. Partial derivative of this capital F, which is this minus g. And then, as you see, fx is at this point, 1 to ln of 5 is 2 over 5, fy is 4 over 5, and fg is always minus 1, because the partial derivative of this with respect to g is minus 1. With this, at this point, 1, 2, minus ln of 5, and 2 over 5, 4 over 5, and minus 1 comes up here to give us the equation of the tangent line, tangent plane. This can be examined in this website. This multi-cells, and tangent planes can be found for this case. For this example, tangent plane can be obtained in this way, and normal line is like this in the parametric equation, and 3D plots are shown in this way. On this surface at this point and plane, tangent plane can be written in this way, and this line shows the normal lines. Okay, and what else? Find the equation and the tangent plane and normal line at this point. For this function, we define the functions and then find the directional derivatives and the normal vectors and equations. Because the vectors and the directional derivatives inner product is equal to 0. That gives us the equation, and at the point, and with the parametric normal, this gives us the normal equations, and this gives us the graph. That we are looking for. This shows us a tangent line and normal lines of the surface at this point. Okay, and that's it. The next is the extrema of multivariate functions. Any questions?